Here we go. All right, so welcome back, everybody. I'm glad you're all here. A couple quick announcements, kind of an overview for the month. Here's the calendar I made for this morning. I will text this to everybody after class so that you can see it later if you want to look at it. Basically, here's the main points I want you to know. Here's today, January 4th. We're going to start Unit 5. And then next week, we're going to have achievement chats with your regular teachers, your independent study teachers. So we're not going to be having class. I said no school. Maybe I should have just said no class because you're going to have a achievement chat, kind of a parent-teacher student conference on these 3 days, Wednesday, Thursday, or Friday. So we won't be having math class those days. And then we have Monday the 17th off for Dr. Martin Luther King Jr. Day. So no school then. And then we're going to have our Unit 5 completed on Thursday the 20th. There we go. So just keep in mind, today, Wednesday, Thursday, we're going to be doing our math class. Then next week, Monday and Tuesday. Then we don't have class these days on the 12th and the 13th. And then on the 17th. And then we'll come back, we'll finish up, we'll review, and we'll take our test on this day. The good news is the month ends the following week. So month 7 ends on the 26th. But we're going to need to start Unit 6 that week on the 24th. So any questions right now about our plan for this month?
Josiah.
Tira.
I just need to finish the Unit 4 post-test.
Sweet.
I'll be able to begin Unit 5. I just need to finish it up. I'm already on, I'm on question 13.
Oh, you're doing it right now?
Yeah.
Okay. Awesome. I'm glad you're working on Unit 4 and finishing it. That's great. You're not alone. There's other folks who are still finishing a unit here or there in the old units. So for everybody, please do what Tira's doing and keep working on your old stuff. And then today's Tuesday. So at 3 o'clock, I'll be back on the link if you want to come and get help again at 3 o'clock today. But for now, though, Tira and all of you, please do work on Unit 5 with me because I don't want you to be lost or confused tomorrow and the next day. So today we're going to start Unit 5 as a group, and I need you to have this information that we're going to do in just a minute when we get started. So if you exit that test, Tira, then later you'll be able to go back in and have your progress still there. So don't submit it, but just exit.
Okay, cool.
Okay, and then if you need it unlocked, and this goes for everybody, if you need your tests unlocked, just write me a message or an email or a phone call, and I'll unlock it right away as soon as I can. Okay. Awesome.
Okay.
But Tira, you're doing great. Thank you for working hard on Unit 4. Any other questions or concerns right now on the plan, folks, for this month? Nope. All right. Well, I'm hoping you're all doing well. Let's get started. So this unit is all about exponential functions. Okay, so we're going to do some notes today, and then I have a homework assignment for you at the end, and then tomorrow will be our first mastery test. So we're not taking the mastery test today, but we're going to do about half of like that lesson, half of all the mastery test stuff today. Then tomorrow we'll finish it and then do the mastery test, the first one. So, anyways, this whole semester, we've dealt with linear functions. Remember, linear means straight line. So that's why all the functions we've been doing so far have been straight lines, kind of like this. And they have a constant slope, meaning it's always up and over or down and over the same amount. Constant slope, it doesn't change, it's constant. So, for example, if we had a slope of 5 over 4, 5 fourths, then that means we're going up 5 over 4, up 5 over 4, up 5 over 4 to get to those points. So that's just a quick reminder on what we've been doing. I want you to compare that to what we're going to be starting for this unit 5, which is exponential functions instead of linear. Give me a thumbs up or tell me on with your mic if when you're ready to move on.
I'm ready.
Tira, thank you. Oh, hang on. Who was that? Levi, did you turn on your camera? Are you good, Levi? Any questions? Are you ready to move on?
I'm ready to move on.
Okay, thank you. Anthony, how you doing? Any questions so far? Brooke?
Nope, I'm good.
Anthony, thank you. Thank you, Anthony. Brooke and Beniam, how you two doing? Any questions so far on this idea of linear functions before we jump into exponentials?
No questions.
Beniam, thank you. Brooke, are you there?
Yeah, I'm good.
Okay. Thank you for the feedback. And Naya, can you hear me? Do you have any questions?
No, I'm
Awesome.
ready.
Okay. Okay. I just wanted to quickly ground ourselves in what we've been doing. So that way it'll be a good comparison to this new style, the exponential. Hey, Bearcat, how are you?
How are you?
Good. Okay, folks, here we go. So let's compare the idea of the linear function to this one, the exponential function. This is an example I have in the graph on the right of our blue line. So just take a moment and look at that with me and examine it. Notice that exponential functions are not straight lines and they do not have a constant slope. It's not always going up and over the same amount. Either in the chat box or if you want to tell me verbally with your mic, how would you describe this shape, this blue line here? It's not a straight line, it's not linear. How would you describe this? Any ideas, any thoughts that you would like to share, please? How about this? Everybody, I want to hear from all of you in the chat. In one word, describe this blue function line. And just type it in the chat. One word that comes to mind when you see this. It's not linear. How would you describe it? I see one response. I want to hear from all of you. How would you describe this? There's not one right answer here. I'm not looking for you to say, like, it has to be this or that. I just want to kind of get a feeling of what you think right now, of what you
I
see.
think one of the things that you could call it would be a undefined slope.
Oh, for sure. It's not the same slope every time, right? So it's not constant. And technically, Levi, remember back to one of our recent units. Hang on, where's my drawer? Here it is. Undefined means it's like a straight up and down line,
Mhm.
technically, because we get that zero in the fraction for the slope. It's like something over zero, like 5/0. And this is undefined. So we got to be careful with that exact word. But I think when you say undefined slope, it means like it's like it's almost it's always
Yeah.
changing, it's always dynamic, right? It's always kind of like not the same as it was before. Like for instance, if you wanted to find the slope between this spot and this spot, this is up a tiny little bit and over this much. But then if you did that over here, it should, if it was constant slope, it should be the same amount, the same up and over. So if we tried the same slope from here to here, it doesn't work. Up this little bit and then over the same amount. Well, this is not on the line. The slope over here is up and over a much different amount, right? Not the same.
The word that I would probably use to describe it would be infinity, because
Ooh, I love that.
it looks like it goes on and on and on forever.
For sure. And good observation. I like that. I didn't think anyone would say that. But yeah, for sure. And we're going to talk about that exact thing at the very end of today. Um, it does go to infinity on the left and on the right. It's kind of going downwards as you move this way. Goes down, right? And then obviously, if we went the other direction, went rightwards, it's going up, 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 up really fast, right? It's not moving down super fast on the left, but it's going up super fast as you move rightwards. So going towards infinity. Good. And then really quick, let me see who wrote in the chat. Oh, Tira, infinity. Yeah, I'm with you. So we'll look at that idea again at the very end today. Let's I want to play around with an example with you. I want to practice plugging in some values for the actual function. So here's an example, and we're going to look at like a generic kind of a y equals mx plus b formula for it later. But for now, let's just play with this example. The basic form of all exponential functions is just like this one here. Y equals 2 to the x power. Here's how we say that. I'll write it out. 2 to the x power. The name of these are exponential. And that x, instead of being multiplied to 2, it's the exponent for 2. I'm going to write that out here as well. The x is an exponent for the 2, for some number. So that's how we say it out loud. 2 to the x power. And just notice that the x is an exponent here. It's not being multiplied like our linear function. It's an exponent. It's a power. Here's a few other examples just so you can kind of see what they all look like. We could also have y is equal to 5 to the x. Power. That would still give us an exponential function. We might have a fraction for the number. So instead of like a 2 or a 5, here we have 1/2 or 1 over 2. Y is equal to the 1 over 2 to the x, or we could say 1/2. 1/2 to the x power. And another one we may come across, or we will come across for sure, is a negative. Y is equal to negative 2 to the x power. And here's how we say that, negative 2 to the x. So whatever like the base is, the 2, the 5, the 1/2, the -2, you say that number and then you say to the x power, -2 to the x. And now I want you to, with all these on the screen at the same time, think to yourself, what do you notice about all these four examples? And also, what do they all have in common? Is there anything they all have in common? And what is it if they do?
They have the same exponent.
For sure, they have the same exponent. They're all some number, some hard real number, right? To the x exponent. Exactly what I was hoping you would notice. So whenever this comes up, whenever you have y equals something to the x, whether it's negative, whether it's a fraction, or a nice positive whole number like 2 or 5, we know already that it's going to be an exponential function and have that curvy shape like we saw back here. Like the blue line was here. A curve that goes up to infinity or maybe down to infinity. We'll see that later, but we know right away if it has one of these forms, then it's going to be a curve, not a straight line. That exponent is our big clue. Okay, now I want to actually plug in some values and show you how we can graph an exponential function pretty fast by doing a little bit of evaluating, plugging in a number for x and solving for y, just like we did with our straight lines. And then we can get a few points, connect the dots, and graph our function. So here's how we do that. I like to use these tables because it's just helpful to organize your work. So here's our example. It's the same function as earlier, y equals 2 to the x. And what we're going to do is evaluate the function for each x value in the table. That just means plug in a number for x and solve for y. And then when we get these points in our table, we'll plot the points on the graph on the right side. So here we go. Let's start by plugging in 0 for x and simplifying and getting our y. So I'll do my work in the middle of the table. On the left, we've got our x values. On the right are the y's, but in the middle, we'll do the actual like work. Y is equal to 2 to the x, but we're plugging in 0. We're evaluating it at x is 0. So it'll look like this, 2 to the 0 power. Now, if anyone's got a calculator or your phone handy and can do an exponent, on this old-fashioned calculator that I have, the exponent button is actually y next to x. It's a little weird. On the blue calculators that the center uses, and some of you may have at home, it actually looks like an exponent, like it should, y to the x. And if you're using your phone calculator, it'll look like this, I believe. Maybe it's a to the b, something like that. I'll put some examples on my screen. I think the Google calculator looks like that, x to the y or y to the x. Try doing that one for me. What do we get when we do 2 to the 0 power? If anyone finds it, let me know in the chat or with your mic. 2 to the 0 power.
I don't know if I did it right, but I got 1.
Ooh. Anaya?
Yeah.
Thank you so much, Anaya. You did it right. Yeah, it seems like it could be wrong, right? It doesn't seem correct, but it's absolutely correct. It's 1. And there's a reason for this. Maybe I should have made an extra screen so we could kind of talk about it, but everything, I'm going to put this in here. This is kind of a special note. Everything to the 0 power is 1. So it's kind of a special case. It's kind of an easy one once you start doing it, like we're starting today. So anytime we're going to do any other functions, like y is equal to 5 to the x, or y is equal to negative 40 to the x, or whatever, it's always going to be 1 when you do the 0 power. The 0 power of everything is 1. Nice job, Anaya, and thank you for sharing it as well. Now, I think we'll go into that tomorrow. If anyone, I think we'll do that. We'll look at why that's true, why everything to the 0 power is 1. For today, though, I want you to just trust me on it and go with it. Tomorrow, I'll show you why that's the case. Now, let's talk about the rest of these. And these we are pretty easy to do by hand as well. If we don't use a calculator, you can do them by hand. Let's plug in 1 now for x. So y is equal to 2 to the 1 power. Now, think about this with me. The exponent is telling us how many times to multiply the 2 to itself. So 2 to the 1 power is 2 times itself just 1 time, meaning it's just 2. There's no more 2's that we're multiplying. The exponent is a symbol telling you how many times to multiply the base, the 2. So this is kind of another quote unquote easy one because anything to the 1 power is just itself. So I'll put that in as a note. Anything to the 1 power or the first power is just the base. It's itself. It's the 2. Anything to the first power is itself. So that's another little kind of gimme, an easy one that will come in handy as we're doing more of these later. So our input was 1, our output now is 2. Okay, let's do the next one. Now things will get a little more interesting. Y is equal to 2 to the 2. Okay, so using that logic, you can try it on your calculators or try it by hand. 2 to the second power means 2 times 2. So now we're oh, go ahead. I'm sorry.
Sorry, I was going to say the answer, but I'm not sure if I'm too much ahead.
What did you get?
I got 4.
Yay! Thanks, Tira. Yeah, 2 times 2 is 4, so our output here is 4. Done. And now same thing for the plugging in 3 and plugging in 4. If anyone did that, what did you get for plugging in 3? 2 to the third power.
8.
8, totally. 2 times 2 times 2 is 8. You can use the buttons on the calculator or just do the multiplication. How did we do it? It was 2 times itself 3 times, and that's where the 8 comes from. And then finally, we get 16 for the last one. 2 to the 4th power. That would be 4 2's lined up, all multiplied. 16. Woohoo! Okay, so here's our points that we're going to plot the points with. 0, 1, 1, 2, and so forth. So let's get an idea of what this thing looks like. So for the first point, 0, 1, that's right in the middle. It's left or right 0, so right in the middle, up 1.
Wait, Josiah?
Yeah.
May I ask, how would 2 to the third power be 8?
Good question. When we expand it out, like let's go back to that box here. We have some space. So 2 to the third power. Well, what does the exponent mean? It's telling us to multiply 2, the base, to itself 3 times. So I write it expanded like this. So if we multiply these together, 2 times 2, the first set, that's 4. 4 times 2 gives me 8, and there's no more 2's there, so we're done.
Okay, I get it now.
Is that okay?
Yeah.
Okay. The good news is when we're doing a problem like this and we're trying to graph it by plugging in x numbers and finding the y, it's always the same base, right? Like in this problem, it was just a bunch of 2's, and we're increasing how many 2's each time. So it's not like you're going to have different numbers being multiplied all of a sudden, like 2, 2, 2, and then a 3. It's always going to be the same base number, the exponent number of times. Another thing you might notice if you look at this y outputs here, it's not the same number we're adding each time. Like 1 to 2 is plus 1, and 2 to 4 is plus 2, and 4 to 8 is plus 4. It's not the same thing being added, but it is the same thing being multiplied. It's times 2 times 2, 2 times 4, 2 times 2 is 4, 4 times 2 is 8, and then 8 times 2 is 16. And that's because we're just multiplying 2's, right? And we're kind of throwing in an extra one for every time we increase x. So basically, it's being doubled every time. The last y is being doubled to get to like the next y in the list. Okay, so back to graphing this. So we've got 0, 1 graphed right here. I'll label that just in case. And then 1, comma 2, not too bad so far, over 1 up 2. And then 2, 4, okay, over 2 up to the 4. And already you should see that it's not the same slope because from here to here and here to here, if I were to connect those as like straight lines between them, one's going up 1 over 1 and the next one is up 2 over 1. So the slope changed right there. And let's keep graphing. 2, comma 4, 3, comma 8. Right here. And then 4, 16. And darn it, I didn't even put a 16 on here. So it would be over 4 and then way up here, just a little bit above our picture. So let me see if I can put that. Really, it would be higher than this, 4, 16. But that's pretty close just to see the picture. So now if you connect these with a curve, we've got our exponential graph. And we didn't graph on the left side. We'll look at those again later, like plugging in a -1 and a -2. And that's it for this. I want to do more of these with you, but for now, I want to look at some other like aspects of exponentials. And in fact, I want you guys to do some of this with me. So unless there's any questions about this so far, which please interrupt if there are, I want everyone to open up another window on their computer or another tab. And we're going to go to desmos.com. You can type in desmos.com/calculator, or you can just go to desmos.com and click on graphing calculator. I want you to type in some of these and get some fast comparisons yourself. So here's 3 to start with. I want to type in all 3 of these. Y is equal to 2 to the x, y is equal to 3 to the x, and then 4 to the x. So let's do all 3 of these at the same time on the same screen and compare. And just so here, let me really quick get you started. I'm going to show you just a quick reminder on how to use Desmos. So stay with me for a moment, and then I want you guys to try it as well. So if you go to just plainoldesmos.com, go click on graphing calculator right in the middle. Now, if you're using a mouse, you might not be if you're using a school Chromebook, but you can click anywhere on the white graph. So like click down and then drag with your finger on the touchpad, and you can move the graph around pretty fast that way. You can also zoom in and out on the right side with the plus and minus. Now to type in a an equation, a formula, a function. On the left side, we want to type over here. Just click in that very top like little bar slot thing right here on the left. Then you can just use your keypad or your keyboard and type in. So y equals 2, and I want to do the x power. Now this can be tricky. We don't want to make it 2x because then it's a linear function. It's a straight line. We got to get it to be an exponent. So how you can do this is down on the bottom, it says show keypad, this little option here. And then we get an option to do exponents, and it's this a to the b. So we click on that, and it basically bumps up the cursor. So it's like going to type in exponents now, and you can type in your x. So there's the first one. We want to click on the left side of the screen and just type in y equals 2. Then we do have to open up the options, the keypad, and you use the A to the B button to make it an exponent, and you type in your x after that. And if you want to zoom out, you can see more of the picture by zooming out, and then you see like just what this thing looks like farther and farther and farther away. Tira said infinity earlier, and then you really get an idea for how infinite this thing is. It's kind of the farther out you zoom, it almost looks like it's going straight up, even though it's not. It's slowly moving to the right. And then leftwards, it's getting closer and closer and closer to 0. It's never crossing over though. To type in your next equations, functions, on the left side, don't erase your first function. I want you to have all 3 at once. So you're going to click right below. So click right below your first function and then just type in the next one, y equals 3 to the x. Like so. And I'm going to zoom in so I can compare my 2 functions together. And I'd like all you to do this as well. Get the first 2 in, and then try doing 4 to the x. And why not 5 to the x? Let's see what happens when we kind of increase that base number, the 2, 3, 4, 5. So let's do 4 to the x, 5, and 6 to the x. Let's do all those. And do this for me. Tell me in the chat when you get those functions typed in, or conversely, if you need help, if it's not working, if you can't get it typed in right, I want to help you hammer that out. So tell me when you get it finished, or if you need help getting something typed in or anything else. Awesome. Anaya, thank you for letting me know. Let's give it a moment while everyone else is getting it as well. Anaya, while you're waiting, look at those different functions you've typed in and see if you can come up with like a pattern of what's changing with the graphs when you make that number bigger, when you make the base larger, like you did 2, 3, 4, 5, 6.
Josiah, I had a quick question.
Tira,
So, what number are we doing it up to exactly?
let's go up to 6. So 2, 3, 4, 5, and 6.
Okay, cool.
Desmos automatically changes the color of the graph like every time you make a new one. So that's nice. And then it shows on the left which color it should be, and then you can see that on the right side, so to compare them easier. All right. Awesome. Anaya, good observation.
So I made an observation and also kind of had a question about it.
Yeah.
So what I noticed is that the higher you increase the number, the more the what's it called? The line on the y-axis moves inward.
Oh, love it. Yes. Yes.
So if you moved it up enough, would it move to a point where it's going like directly on the y-axis?
That's a good question, and a great observation. So, really quick, let me just enunciate what you already said. I want everyone to hear that. Levi noticed that the higher the number gets, the 2, 3, 4, 5, 6, the higher that base gets, the closer our line is getting to the y-axis. And then that follow-up question is there a point, like, is there a number where it lines up straight on the y-axis, like perfectly? The answer to that is no, because it's always increasing to the right, even if it doesn't even look like it. So I'm going to jump ahead. Like, let's put in y to the 6 to the x. So I'll be caught up with all of you. So there's my y. And so that pattern is correct, like what Levi pointed out. Even my 6 to the x is even closer still to the y-axis. It's getting more and more straight looking, right? But let's jump ahead super much. Let's do like y is equal to 1,000 to the x and see what it looks like. 1,000 to the x. Ooh, okay. So there's 1,000 to the x. It's my inner red one. Try that on your screen or just look at mine. And it's still not on the y-axis, right? It's closer. It's still not there. Let's try an even bigger number. I don't know, 5 million. Y is equal to 5 million. Yeah, that's 5 million to the x. It's still not there. Like, it's still just slowly creeping to the right. And it's kind of cool, Levi, that no matter what you make that number, um, you can make it bigger than 5 million and it's going to be closer to the y-axis and it's still not going to reach it. And it's still never going to be a truly straight line. It's just, it looks straight, but it's slowly creeping rightward to infinity. And it's going to be moving up to infinity. And then Anaya pointed out in the chat, I hope it's okay that I say this. She said that they're all meeting at that same point right here. You should all see that on your screens too, or if you're looking at mine, they're all meeting right here at 0, 1. They're all crossing the y-axis at the same exact place. And why is that? Because no matter what our base is, whether it's 2, 3, 4, 5, or 6, or even 5 million like I did, remember when you plug in a zero power for any number is always 1. So no matter what our base is, as big or little as we want to make it, it's always going to be crossing right there at 0, 1. Another thing I want you all to notice before we move on is, regardless of the size of your base, with the number that you chose, they're all, like Levi pointed out, they're all kind of getting closer to the y-axis as they move up on the right side. And they're all getting closer and closer and closer to the x-axis as they move leftwards. And yet they never cross it. They're going to be getting closer and closer and closer while never like reaching it. And another third final thing I want you to notice is they all basically have the same shape. They're all curves that are almost flat on the left, but they're not. They look flat, but they never really reach flatness. They never reach 0. And then as you move right, they get steeper and steeper and steeper. And depending on what the base number is, That determines like if it's being doubled or tripled or quadrupled or whatever. So for our first example we did, it was 2 to the x. All the y values are just being doubled. 2, 4, 6, 8, 16. I'm sorry, 2, 4, 8, 16, and then would be 32. Double that, 64. But if our base is 3, like 3 to the x, then it's being tripled. So it would be 3, 9, 27. So it's like times 3, times 3, times 3. So the base determines like how steep it is. Kind of like slope, but not exactly because it's not the same exact up and over. It's always being doubled or tripled or quadrupled or multiplied by that base, basically. Okay, now keep your Desmos screen up. I want to do something similar but different with you now. So keep your Desmos up, but I want to talk about adding or subtracting a number to the function. So do this with me. I want to, let's go ahead and delete most of your graphs. Let's keep up y is equal to 2 to the x. So to delete them, you can click on those big old gray x's, and that'll just get rid of it fast. So I want to keep up just our original 2 to the x. And now let's try adding or subtracting numbers to the outside like this. Y is equal to 2 to the x. And then let's do plus 3. And then a third one I want you to graph is, we'll keep it as 2 to the x for all this, but let's add and subtract different numbers. So let's do y is equal to 2 to the x again. And we'll do plus 4. And then let's also try a minus 1, a negative one. So y is equal to 2 to the x, and we'll do minus 5. And one note I might need to mention is if when you're typing this in to do the plus or minus, um, after you've done your exponent of x, I think we need to click to the right with your direction arrows to kind of get out of the exponent. Otherwise, it's going to be a plus or minus up with x. We want the plus or minus number to be down with the original line of writing, not up in the exponent. Check out my screen to see an example of what those look like. And if you need help with that, please tell me. I want to make sure we're all able to use this program. Play around with it. Don't just put in the ones I made. Feel free to do as many or different ones as you want to. But I want you to put in some adding and subtracting numbers, 2 to the x plus anything or minus anything. What do you see that's, I guess, different this time comparing these graphs when we have different adding or subtracting numbers? Anything stand out as different in the pictures, in the graphs themselves?
I noticed that when you're using subtracting or when you're subtracting numbers, it goes to the side where it has the negative numbers on the graph.
Yes. It go like for instance, I have 2x minus 5 and it's going to minus 5 on my graph, right? It's reaching all the way down to that far. Is that what you're
Yes.
Okay. Yes, Tira, I'm glad you saw that. Notice this time they're not all meeting at the same spot like they were for our last examples. This time the y-intercept is changing just like where it's reaching is changing. So for example, our base starting function is always going to be the 2 to the x. Let's think of that as kind of our parent graph, our parent function. When we mess around with that and we change it by adding 3, I'm going to get rid of all my graphs except just those two. So comparing 2 to the x and 2 to the x plus 3, it's moved up my y-intercept by 3 units, 3 squares. So looking at the old one, it was crossing the y-axis or the y-axis at 1, but now it's crossing at 4. So it's like I took my original function and just kind of dragged the whole thing upward 3 units. Instead of crossing at 1, now it's crossing at 4. And let's go back to the minus one Tira pointed out. So y is equal to 2 to the x minus 5. Okay, so for this one, its y-intercept is at negative 4. So it's like my original was at 1, and I went down 5 units. 1, 2, 3, 4, 5. So 1 minus 5 is negative 4. So it's like taking the original parent graph and dragging it down 5 units. The shape of these is actually the same exact shape. It's just been moved up or down by that number of units. Plus 3, minus 5, plus 4. And then where it's trying to reach has also moved up or down as well, like what Tira pointed out. So for looking at just the original again, my 2 to the x, it is reaching the 0 line. It's reaching 0 and it's never crossing over it. But when I do the plus 3, now it's reaching the 3 and it never crosses over. It's getting closer and closer and closer to y equals 3, but it never goes under it, never like meets it. It looks straight here, but it's actually getting lower and lower and lower each time. And then same for the negative version. Now it's trying to reach negative 5, but it never quite makes it. So if we've got our generic exponential function, like 2 to the x, and if we add or subtract a number like we did here, it's going to change the y-intercept, and it's going to change where it's trying to reach, where it's getting flatter. However, the basic behavior is still the same. It's still like approaching a number on the left, and it's reaching up to infinity on the right. All right, it's almost 12. So I want to show you guys another thing. And why don't you all just come back to the main screen with me if you're not already? I wanted to have you do this like we've been doing it, but I want to, since we're low on time, I'm going to show you the last couple things. So what happens if we make the whole thing a negative? So let's try this. I'm going to keep up my y is equal to 2 to the x, but I also want to add in a negative version. Okay, what's happening? Crap. Okay, I guess I lost connection. Can you guys hear me okay?
Yeah, I can hear you.
All right. Thanks, Tira. Sorry about that, everybody. What I was saying is I wanted to show you all one more thing before we end today, and it's almost time to end. So if you haven't already, come on back to the call instead of using your own Desmos. I want to show you something, and then we'll go for today. So what if the whole function was made negative? So I'm going to keep up 2 to the x here. And also, let's put in negative 2 to the x. So in green, we see the negative exponential. It's kind of a mirror image going downward instead of upward. But notice how everything is like mirrored or symmetrical is the word I'm looking for. Symmetrical from top and bottom of the x-axis. So for instance, here's a point 1 comma 2 that we found earlier when we were plugging in stuff for the same function. 1 comma 2. And then right below that, we see 1 comma negative 2.
Josiah,
Yeah, please.
I don't know if anybody else can see this, but I can only see your face. I can't see your screen.
Oh my gosh, I'm sorry. There we go. Thanks for telling
Okay,
me.
now I can see
My
it.
bad. It's because I didn't reshare. All right. First day back. I need some time to get used to it, I guess. Sorry, guys. So here's 2 functions, the 2 to the x and then negative 2 to the x in green below it. Now, if we were plugging in points here, we would use our table like we did earlier and plug in, x is 0. 2 to the 0 is 1. But since this is negative, then that would give us negative 1. And that's why our y-intercept is down at negative 1. And it's kind of like heading downward instead of upward. The same rules that we talked about earlier still apply if this were negative. So let's do a couple quick comparisons. So but I'll increase the base number again. So let's do negative 3 to the x. And like Levi pointed out earlier, my 3 to the x is getting closer to the y-axis in the middle. Same thing will happen when we increase it still. And there in black, we see negative 4 to the x getting closer to the y-axis, right? Getting more straight almost, but never going to quite achieve it. It's going to always be heading to the right still. Negative 5 to the x. So if we make it negative, it's still an exponential function. Only difference is it's heading down to infinity instead of up to infinity, heading towards like negative infinity. But the higher we make that number, the base number, the kind of tighter the whole thing gets. It's kind of hugging the y-axis more and more and more, as you guys have been pointing out. Okay. Last thing I wanted to just show you and mention is the end behavior. And Tira kind of pointed this out in the beginning. End behavior, and I've been talking about it as we've been going. The end behavior of the function is describing what the function is approaching towards the left and towards the right. So when I say, or when the Edmentum or any math class you're ever in, when they talk about end behavior, what we're talking about is like, what does it look like the graph is doing towards the left and towards the right? So here's a couple quick examples of that. And now this is, the same function we've been dealing with all morning. So this is y equals 2 to the x. Now, as we move towards the left, as x approaches negative infinity, or just so you could say moves left, as x moves left, as x approaches negative infinity, What's our blue line doing? It's approaching zero. It approaches zero, or y approaches zero. It's getting closer and closer and closer to this line, right? The x-axis, zero. Now let's look at the other side. As our line moves rightwards, as x approaches infinity, positive infinity, what's the graph doing? It's getting higher and higher and higher. Y is approaching infinity. It's like getting higher and higher and higher. It's not reaching some number where it's stopping. Y is approaching infinity. So as we look towards the right, what's happening with the line itself? It's getting higher and higher and higher. Just like when we look towards the left, what's happening with the line itself? It's getting lower and lower, but it's capped off at zero. Kind of like a wall or a barrier. It's capped at zero. Go ahead and take a picture or make a quick note of this, and I guess it's time to go. I wanted everyone to have a homework assignment today. It's 4 questions. And I know the end of the lesson was a little rushed and I've lost connection and I'm sorry about that. But I think you have seen enough and done enough today to try doing this. Here's our homework. Page 11 only in the first tutorial, Unit 5. Here's what it's called, Graphs of Exponential Relationships. I want you to do all parts. It's only 4 questions. So play around with that. If you need to review, the pages leading up to 11 are going to cover the stuff we need to know to just do page 11. And it's basically the same thing we did in class. So feel free to use that tutorial as extra review. I want you to all do this first 4 questions on page 11. Don't have to do the whole tutorial, just page 11. Tomorrow, I'm going to finish this lesson entirely, and then we'll do the first mastery test, okay? Thank you all for coming. It was really good to see and hear from all of you. Have a great rest of your day. Thanks, Bearcat. Bye.
I had a question.
Yes, please.
So I noticed that on the 24th we're all gonna start going back to school in person.
Yeah.
So are we gonna do the same for math classes too?
So I wanted to talk to you guys about that, but I can't force you all to come back. So if you still don't want to, what I'm gonna do is not you, but just anybody. If students aren't ready to come back in person, considering COVID and everything, I'm going to be recording lessons like normal, putting them up online. I'm going to do my best to try to make it interactive for online and in person at the same time, but it might end up being kind of like watch the lesson after it's done, and then you do it, and then um, at home. So it'll be kind of asynchronous. Like you'll be watching the video of what we did in class, and then you'll be trying to do it on your own afterwards, from home.
Okay.
I'm not forcing everyone to come back. I would love it if you are able to, just because I think we'll get more done, and I think it'll probably be more meaningful for students that are able to come in person. But yeah, so I'm going to be doing both. Like you'll still be able to attend even if you can't come back in person 4 days a week.
Okay, cool.
Yeah, I didn't mean to scare you, but and I know that like COVID and everything is kind of scary, and maybe people aren't ready, so I totally get that. But we're doing health checks here, and testing for free is available. You can get tested like weekly by the school if you want to. So we're taking a lot of precautions, and I think we're doing our best. And I think it's time for us to get back in person. And honestly, I did want to like force everyone to come back for class, but I'm not going to. So that's all good.
Okay.
Okay.
All right. Thank you for letting me know.
Yeah, I was going to talk about it more tomorrow and in the weeks going forward too.
Oh, okay. Okay, cool. Thank you.
Yeah. Thanks, Tara. You take care.
You too.
Any other questions, you three, Anaya, Beniam, or Brooke?
I have one.
Yeah.
Can you, or do you mind going back to the page you were just on with the infinity? Because
Oh,
I was going to take a picture, but it wasn't, it was just taking a minute, so I couldn't
course.
get it.
no problem.
Okay.
No problem. Can I show you one more, even though it's after 12?
Sure.
Okay, let's do one more together real quick. So here's another one. This is, what is this? The function would be the same shape, it's 2 to the x, but it's been dragged upwards. So I think what we're looking at is 2 to the x plus 3. And how do I know? Well, where does it look like it's getting flat? Right here, right? And if we look over, that's basically that 3 right there. So here's our actual function. Now let's talk about the end behavior. As x is moving leftwards, so as x goes to negative infinity, what's y doing? Y approaches 3. Not 0 this time, right? Because it's not reaching all the way down to this line. It's stopping at the 3 line. Y approaches 3. And then same as last time, as x goes to positive infinity, what's y doing? Well, y's just approaching infinity itself. It's getting higher and higher, never capping out. So y also is going to infinity. So it didn't change the right end behavior, but it did change like the left end behavior. Just something to keep in mind. So feel free to take a picture of this one too. And we'll probably start tomorrow with a little review and maybe do more of these together. And then there's a few more things I need to do with you. And then we should be ready for this lesson all the way.
Thank you.
Yes, absolutely. Have a good day, Anaya.
You too.
Bye.